Hello. Am I audible? Please, anyone confirm it.
Yes, audible.
Okay, fine. We will wait for 5 6 minutes, and after which we will start. Okay.
Okay, sir.
डॉक्यूमेंट में अच्छी स्टार्ट हो रहा है
ये नहीं तो ज्वाइन में छोड़ देना है खाली के
Kindly mute yourself. Okay.
बोली तो रहती ना तो पक्का बोल देते हैं आगे
ज्वाइन हो
start करें
जाए
यार
ना अभी स्टार्ट
Ashutosh, please mute yourself.
डाउनलोड करना है क्या
म्यूट कर दो
So good evening, everyone. So my name is Abhishek Munshi. I am a research scholar at IIT Jodhpur, and I am working at the Transportation Electrification Lab. So I will be your course tutor for this uh, design of power electronics, and this is the agenda for this week. We will discuss a little bit about the application of power electronics. If you go through the lecture of this week, then you can already understand that this course will be an advanced course of power electronics, where we will not discuss about the basics like how the MOSFET will function, how diode will function. Okay, so we'll move into the directly into the power electronics converter and the designing of that. So this week we will design. We'll discuss about the DC-DC converter analysis and a little bit about the edge-based analysis. Okay. So yes, uh, if you have anything to say it loud. Okay. Is it clear now? Have you able to hear it? Okay. Okay, fine. So we'll discuss about the application of power electronics and what is power electronics basically. So from the email, I shared a block diagram. Here you can see that uh, power electronics is basically the part of the electronics which will basically deals with the high power energy. Okay. So uh, obviously there will be a source which will be a AC or DC, and there will be an electronic circuit by which we can convert it into DC or AC. Okay, and definitely to make it stable at the all time at the load, so we need an controller. So we need to feedback the output via controller to the source, so that it will maintain it output all the time. So how many types of converters are there? It may be DC to DC. The source may be DC. The load may be output may be DC. So that kind of converters are called DC to DC converters, also popularly known as DC chopper. The source may be AC, the output may be AC. That kind of converters are called AC to AC converter. For example, matrix converter. The source may be AC and we will get a DC. And that kind of converter, we already learned it from the basics of class 10, 11, that is a rectifier, right? And if we have an input of DC and we're getting an AC, that kind of converters are called inverter. So in power electronics, the DC-DC converter, the inverter, and the rectifier, these three are very important things we have to deal with every time whenever you're in power electronics. Yes. Anyone have any doubt? So Prabhat, the voice is clear, right? Right?
yes sir voice is clear now
Yeah, yeah. So basically, what I'm saying that in case of the power electronics, we mainly deals with converters which are DC to DC converters, inverters and rectifiers. Mostly we're using with that, and in advanced case, we'll obviously use AC to AC converters. In book, we will see that AC to AC converter ends with cyclo converter. But if you are doing power electronics, if you're going to design power electronic converters, then you have to start with matrix type of converters in AC to AC. Okay, so what are the applications of power electronics? So basically, uh, power electronic converters are used in motor drives, in the the most famous function is that we have to design switch mode power supplies. uh, any kind of power supplies which we are using for the charger, in which there will be definitely a power converter. Okay. And in home we obviously use some kind of inverters, UPS, and that's also built up of some kind of converters. In renewable energy, whenever you're using PV solar, then there definitely there will be a DC-DC converter by means of where giving the voltage output to a battery to charge it or any kind of function. So on that case we basically use a DC-DC converters.
सर थोड़ा हिंदी में बोलिए ना, समझ नहीं आ रहा।
See, this course is designed for in a way that we have to deal with English, and at the end, if you have any doubt, we can discuss it in Hindi. But according to the protocol of this course, I am just a teaching assistant of this course, and we are advised to go through in English. So I'm trying to try to understand, and if you have any basic doubt over there, then we will discuss it at the end of the class. Okay.
ओके सर।
So see that and other functions of power electronic converters are recently the most popular function is that the wireless charging systems, the wireless chargers, in which HB DC-DC converter is used, where we are wirelessly sending the power from one end to another. That is also wire power converters. Uh, so before moving into the converter analysis, we have to assume some basic things that that we have to deal the converter design obviously in steady state, not in a transient state. Okay, we have to deal in the steady state. So in steady state, we have to go through two basic principles. One is inductor volt second balance, and the another is capacitor amp second balance or charge balance. Okay. And while modeling a converter, we always deal with the small signal approximations. Okay. And obviously, when we are deriving a converter circuit, we will hope that we will always consider it as an ideal circuit, not a non-ideal circuit. So in case of the non-ideal circuit, we have to deal with some kind of non-linear controls and non-linear diagrams and so on. Okay. So here we will basically deal with the ideal circuit. So I will discuss some basic things, after which we will solve some problems, and we'll move on in that way. Okay. So the first thing which we will discuss is the volt second balance. Okay. So what is a volt second balance basically deals with that. If you see here that this is the voltage across a inductor. Okay. And is seeing that the this if you have an inductor and IL is the current and VL is the voltage across it, then obviously the response of it will be like this. So what volt second balance defines that the average inductor voltage will be obviously zero. The average inductor voltage at any case it remains zero. So if we apply the volt second balance for any converter analysis, then what happens? Yes, visible, right? The screen is visible, right? So,
Yes, sir.
so whenever we apply this volt second balance, we always have to apply volt second balance for the DC-DC converter analysis and all. So, uh, the uh, the fundamental thing behind it that is the see I'm written in that way that whenever the voltage across inductor when on, the T on time plus the voltage across inductor at off time will equal to zero. The average inductor voltage always remains zero. That means that the on time voltage and the off time voltage, the sum of which will definitely zero. From the curve, you can see that the on time voltage, the this area A and this area B will definitely cancel out.
भारत माता की जय। सर क्यों नहीं चल रहा?
Extremely sorry for the network issue here at our IIT. There is a change in the server, so it got happened. So I'm sorry. So where I was there, I was at amp second balance. I'm saying that in case of the amp second balance, the average capacitor current will remain zero. Okay. So if anyone had a mute, please mute yourself. Yes. So I was saying that the if you apply amp second balance, so that will be the average capacitor current will remain zero. So the turn on current and the turn off current of across a capacitor, if you are giving a set duty across it, then it will be zero. So if you have any doubt regarding the amp second and volt second balance, you can ask me, and after which we can move into the forward to the DC-DC converter analysis. If you have any doubt, you can ask. Feel free to ask, okay? Because this is very important for analysis of any kind of DC-DC converter.
Please explain once again, sir.
Screen is not visible. Is it is not visible to everyone?
Sir, please explain it twice. Actually, we are not getting that what actually means. Means application. You can say like application wise or something.
If you are comfortable in Hindi, you can ask me in Hindi, okay?
हाँ सर, मैं कह रहा था इसको फिर से बता दें, जैसे हम नहीं समझ पा रहे कि एक्चुअली इसका मतलब क्या हुआ।
किसका?
जैसे ये तो आईसी ऑन प्लस ऑफ
देखो,
इक्वल टू
ये मतलब ये है कि इंडक्टर के अक्रॉस तुम्हारा वोल्टेज जो रहेगा, एवरेज वोल्टेज वो जीरो होता है, और कैपेसिटर के अक्रॉस एवरेज करंट जीरो होता है। तो इसको हम जब कोई कन्वर्टर एनालिसिस करेंगे, हाउ कुड वी अप्लाई इट? वी अप्लाई इट इन दैट वे दैट IC on, that is the T on time, when up to the time which the capacitor current remain on, plus the time up to which the capacitor current remain off, the sum of it will be zero. Okay. So this is what I am trying to say. So whenever we apply it in a converter, you will able to understand more about it. Okay, just know the principle first, that this is volt second balance and this is amp second balance. So whenever we apply for a converter, that will be more easier to understand. Okay, so we definitely will move into that and solve in that way. Okay, anyone else? Okay, fine. Then we're moving into the types of DC-DC converter. So basically, DC-DC converter are of three types. One is buck converter, which is a step down converter. Okay, so in which what happens, whenever you're giving an input voltage, the output voltage will be less than that of it. Okay, and next is a boost converter, which is basically a step up converter, in which if you are giving a voltage V in, the output voltage will be greater than that. Okay. Another is buck boost converter, in which depending upon the duty, it may be step down, it may be step up. Okay. As you see in the screen, that for a buck converter, I said that the input will be suppose 15, the output will be 5. For a boost converter, for a 15 volt, the output will be 20 volt. Okay. For buck boost, it may be 5, it may be 20. Okay. So this is the structure of a buck converter, and this is boost and buck boost. Okay. So can anyone tell me what is the similarity between these three?
Same switches were used.
Sorry.
all are DC-DC
All
In
are
all the
DC-DC.
converters, same switches are used. The components are same, only the arrangement is different.
Yeah, definitely. That's exactly right. So if you see that there is a pattern over here, that the switch, diode, and the inductor combination. See, here also this combination is there. Here also it is there. Okay. So if we consider this as a canonical structure, please unmute yourself if you have don't doubt. So if you consider this as a canonical structure, you can see that if you rotate it in this anti-clockwise direction, you will get this one. And if you rotate it again in this anti-clockwise direction, you will get the buck boost converter. So this is a pattern you can remember for simply understanding what kind of converter is it. So if you go through this canonical structure and moving it in an anti-clockwise way, you can see that the buck can be converted into boost, boost to buck boost. Okay, is it clear? Is it clear to everyone that this is a canonical structure? If you consider it and move it in anti-clockwise, then we will get every converters over here. Okay, so this is just a trick to understand the structure of the converters. And this is the, in this converter, you can see that there is a switching structure, and this is the output. And this, in every converter, there is an LC pattern. This is kind of a filter. It works as a filter. Okay. In boost, the inductor is at forward because firstly it's boosting the voltage. Okay. So in this way, they are arranged. Fine. So we will focus on the buck converter and discuss about the buck converter according to the course structure right way. So in the buck converter, we see that there is a switching circuit. The number one, I labeled it in that way that this one is the switching circuit. This LC is the filter circuit. This is basically a low pass filter, right? What is a low pass filter? Can anyone say what is a low pass filter?
It allows the signal below the level of bandwidth frequency.
Yes. Basically, it's allowed the lower frequencies than out of the bandwidth if you're defining a band, right? And it reduces the higher order frequencies. So this is a DC. So we know that if you have a high frequency output and we are neglecting the high frequencies, from the Fourier analysis, if you can see the FFT of any high frequency, there will be a DC plus the rest component. So if you are neglecting the rest component, then we will get the DC of it. That is basically the average of it. So in this way, the LPF, the low pass filter works. Okay. So the first structure one, that is a switching structure, the switching circuit in which the regulated energy, if you see that, the flow from the input to the output by means of the turn off and turn on. If we have to, for this switch, we have to apply a gate pulse. Right. If you are using a MOSFET or IGBT, you have to apply gate pulse. So the gate pulse should be like this. So this is the on time, this is the off time. Okay. And the duty is the turn on time by total time, or that is turn on plus turn off. So based on a specific duty, we are getting the output and we are giving the pulse into the switch. That may be a MOSFET, that may be an IGBT. Okay. Next part is a low pass filter that basically smoothen the circuit. Uh, if we don't apply the capacitor properly, then we'll see that there will be a voltage ripple, lots of voltage ripple. If you desire to get a 5 volt, suppose we desire to get a 5 volt, but actually we will get like this. So to avoid this ripple, more we are properly design a capacitor over there and inductor. For the inductor is used for ensuring that there will be less ripple in the current, and the capacitor for ensuring that there will be less ripple at the voltage. Because if you have so much ripple, the noise, then it will affect our load. If it is a battery, if you're charging through this converter, fine. So this is the characteristic of a, we'll discuss about the behavior of a buck converter. This is the on time, this is the off time of the switch. So what happens if we apply that amp second balance which I was discussing over there? So if I add duplicate this light, okay, fine. So if we delete it, okay, fine. Please turn off your mic, okay? So this is the case when the switch is on, right? Right. So when the switch is on, the equivalent circuit of this buck converter, if you copy it, let me copy it. Okay. So okay. So when the switch is on, uh, when this switch is on, then the circuit will be like this is our input voltage, and there are inductor and our load, right? Because then that time the diode is not conducting. Okay. So if this is our input V in and this is my output V0, the voltage across the inductor is VL, right? So during the on time, if we apply KVL here, we'll see that the VL on is equal to V in minus V naught, right? Similarly, if you consider the capacitor here, the current across the capacitor IC on will equal to the current across inductor minus the load current. Okay. In a similar way, if the switch remain closed, so when the switch remain closed, the diode will conduct. When switch is off, so this is my load inductor. So in that case, what happens when the switch was on, the inductor gets charged, and now the inductor energy will be free wheel across this diode. So in many times this diode can be referred as a free wheel diode. Okay. So in that case, what happens? The inductor charge energy will be discharged across this path to charge the battery, the capacitor, and there will be a definite voltage across the load. Fine. So now if we apply KVL across it, this is plus, this is minus. From negative will go like that, plus minus. So it will be VL off plus V0, that is equal to 0. And similarly, the current across capacitor IC of is equal to IL minus I0. Okay. Krishna Priya, can you kindly mute yourself? Yes. So, so this was the case that this if you apply KVL during the on time, and this was the case when we applying KVL during the off time. Okay. So now, if we add a slide, now if we apply the volt second balance, what was the volt second balance? What I said that the voltage across inductor during on time plus the voltage across inductor during off time will remain 0. So during on time it was V in minus V0, right? So it is V in minus V0. And if you see that if this is my on time period, this is my on time period, and this is my off time period, and I define duty as T on by T on plus T off. Okay. So this is T on by total time. So the T on, the on time will be dt. Definitely, then the off time will be 1 minus of dt. Okay, clear? So we will put on the on time dt plus VL off, which we calculated as minus of V0. Okay, so minus of V0, 1 minus t, that is equal to 0. So it will be V in dt minus V0 dt minus V0 t plus V0 dt, that is equal to 0. So this will cut, ultimately it will be V0 t, that is equal to V in dt. Okay, so V0 will be dV in. So in case of a buck converter, the output voltage is just duty times of its input voltage. Okay, so if you are asked to calculate the duty of a buck converter, then that will be V0 by V in. So suppose there is a input voltage of uh, 5 volt, and we're assumed to get around 10 volt, then what will be the duty?
Two, two.
2. So basically this will not work as a buck converter. Why? As I said, that buck converter will step down, right? So this is an impractical question. Okay, this will be practical if we ask that there is a V naught of 10 volt and we are assumed to sorry, there is a V in of 10 volt and we assume to get V naught of 5 volt, because in that case that will be stepped down. Okay, so in this case what will be the duty then? That is 5 by 10, 0.5. Remember one thing, that always the duty will remain,
0 to 1.
yeah, 0 to 1. Okay, fine. So this is how we derive the output voltage of the uh, buck converter. And now we are applying the amp second balance. Okay, let me apply the amp second balance, or charge balance, you can also say that. So in that case I said that the capacitor current on during the turn on time plus the capacitor current off during the turn off time will remain 0, right? So if you see what was the result, IL minus I0, okay, in both cases we get same. So this is IL minus I0 of dt plus IL minus I0 of 1 minus dt. Okay, so from here you can see that IL minus I0 equal to 0. So the inductor current will be always, in case of the buck converter, the inductor current and the load current will be equal. The load current and the inductor current. Inductor current in the sense means the average inductor current. The average inductor current will remain always same. Fine. Any doubt up to this? I will share the slide, so don't worry about it.
So I have one question here.
Okay, ask me.
Uh, um, is it important to know how to derive those equations?
No, it's not important, but if you remember, if you try to mug up those equations, then whenever you will solve something, right? Whenever you will solve any problem, then that will be difficult for you to always mug up lots of hundreds of equations of one converters, right? But if you are only designing a converter, then definitely you can go through the data sheets and you can put that equations and solve it. Okay, you don't have to remember those equations all the time, but
Okay.
the way I am discussing, I hope it will be more easier to understand and don't have to mug up those equations, right? So
Okay, sir.
okay, fine.
Thank you.
Sir, where we can find this PPT?
I will share it to the NPTEL, and they will share it with you after 1 week or uh, 2 week. Okay,
Okay, sir, thank you.
so try to note down if possible. And okay. Okay, fine. So now we will derive the ripple current in an inductor. So that is also I will go through in a normal, in a layman way that you can understand. You don't have to mug up. You just remember it in the way I'm discussed. And after which I will go through the way the books are given, that the average inductor current, the integrations and all. Okay, so I will discuss in that way also, but I try to discuss in a more simpler way first, that you able to understand the thing properly, then I will go through in that way also, and you will judge that which method will be more easier in future to understand. Okay, so next thing, if you have any doubt up to this, you can ask, and we will move into the ripple current calculation of the inductor. Okay, so I consider that you don't have any doubt. So ripple current inductor, obviously, that is delta IL. So basically, we see that the VL on was equal to the V in minus V0, right? Is that clear? Is this equation clear to everyone? See, the voltage across inductor can be represented as L. Okay. L T inductor current by dt, that is equal to V in minus V0. Okay. So this change in this inductor current is basically the ripple current. So you can write it in that way. Delta IL by dt is basically the on time, that is the duty into the t. Okay. So this is basically equal to V in minus V0. Fine. So now if we have to calculate the delta IL, then that is basically V in minus V0 by L into dt. Fine. Now we know that V0 is basically dV in. So replace it in that way and we'll see that that is d common 1 minus of dV in by L t. Now the t, that is the total time period, can be replaced by the 1 by switching frequency. So ultimately we can get V in FSWS. Okay. So this is the equation we can derive for a buck converter ripple inductance. Is it clear?
Sir,
Yes.
can you tell it once more? The derivation.
See, I what I said that during the on time of the inductor, the voltage was V in minus V zero. So the voltage across an inductor will be L di dt, right? So this di dt means during on time, this dt means duty into time, t on, okay. And this is this change in current is, if you have see the other slide, I will show that the inductor current will like this. So the change in this current will be the delta IL, okay, the ripple current. So we
Okay, sir.
replaced it with delta IL by dt. So after which I just derived it in the way it follows. Okay.
Okay, sir.
Okay. Okay. Then moving to the next slide. See that what I said already is it's in the uh, curve, that there is, if you have considered it in that way, that there is a duty cycle we are giving, then the average value of it will be the output voltage. So we can do it in that way. If you can integrate it, we can see that you will also get V0 equal to dV. So either you go through integration or we go through the m second balance, that is basically in integration itself, right? The whole second balance. As I said in the first slide, that the area across uh, the on time and the off time will be cancelled out, right? For so we applied that concept in a different way. Okay. So if you go through in that way, that uh, this is I'm just revising for the this week lectures in the way this week lecture goes on. If you this is a converter analysis of the buck converter in continuous conduction mode. Okay. So if you see during the on time, the if you apply the KVL, we'll see that VL is equal to VN minus V out and IC is IL minus I naught. Okay. So this is what I derived already. Okay. And during the off time, we'll see that VL is equal to the minus V0 and IC will remain IL minus I0 because the capacitor will be always charged, right? Whenever the switch on, that it will remain charged, and whenever the switched off, it remains charged itself, because the inductor current will freewheel across this diode and try to remain the charge across the capacitor same. So that's why you're getting an output voltage. Okay. So if you integrate the inductor current, we say that according to the volt second balance, total integrating time, uh, if you integrate the voltage across this time, that will be 0. So that is basically V0 equal to dV in. You can get it in that way also by means of integration or by simply in an algebraic way I discussed. Okay. So this is the buck converter analysis of the curve. Uh, so many times it was asked questions through the uh, graphical method way. So you can see that during the on time, from here, this is the duty. This is the on time. In on time, the current across the inductor is rising. When it off, then the inductor current will discharge across the diode. Again, when it on, the inductor current will try to on. Okay. And the voltage across the inductor will be, we discussed that we calculated it as V in minus V naught. During the off time, it will be negative of V0. Okay. And the voltage across the diode will be V in for the on time, and for the off time, the voltage across the switch will be V in. Okay. And this is how the switch current, when during the on time, the current across the switch will increase and then it's off. And whenever the switch remain off, the diode will be conduct because there's a reverse bias, and so during the off time, the diode will remain, that current will discharge through that. Okay. So this is the graphical analysis of this buck converter. Fine. So what are the roles of this LC filter? Basically, yes.
Sorry, sir, can I disturb you for a minute?
Okay.
You said something about is it the average inductor or something?
Yeah, yeah.
Yeah, so where do we use that average inductor value? I'm not
See,
sure if it's average inductor or average something.
average inductor voltage, I said. Okay.
Yes,
The,
average inductor voltage. Yeah. So on the past PowerPoints that you just showed us, where do
yeah.
we apply that average
See.
inductor voltage?
That was the first slide where I discussed this. That average inductor
No.
voltage remains zero. Okay. So I
Also,
said,
okay.
right. So that means that the on-time voltage and the off-time voltage will be, for the sum of it will be zero, since from the curve you can see if you integrate this also you will get that. Okay. So we apply it over here for the buck converter. The average voltage remains zero, and we get the nature of the buck converter's output voltage.
Okay. No, that's clear. Thank you, sir.
Okay, fine. So we are here. So we discussed the role of the low pass filter over there, that basically it cancel out the ripple current and ripple voltage to make it more simpler. Okay. So right now I'm discussing that what is basically the continuous conduction mode and what is the discontinuous conduction mode. Okay. See, we can define it in the way the inductor current, that during the continuous conduction mode we can see that uh, the inductor current will charged, and then during the off time it will discharge, and again when the switch on it will charge at the same time. But in case of the discontinuous conduction mode, there will be a flip of time. On that time the inductor current will remain off, and after a certain time it will getting on. Okay. So this momentarily the drop to zero during the part of the switching cycle is called the discontinuous conduction mode. We can see that the current across the inductor will not rise up whenever the switch is on. So this is the transient analysis of the converter, that in a practical converter, in a practical switch, if you switch on that, then it will not getting on again whenever you re-switch on it. Okay, so that was the discontinuous mode of conduction. So if we are applying, if you derive the equations for discontinuous, then we have to consider this second t of time also. Okay, so on that time the inductor current will be zero. Okay. So since this course we discuss about the CCM, so we will more into the CCM only. Okay. So as I discussed that how we will calculate the inductor current, how we will basically size the low pass filter inductor current. Okay. So I said that the in voltage across the inductor will be LDI dt, and in that way we can able to calculate the inductor value. So the aim of this course is to design a converter, right? So basically how we design the inductor, how we design the capacitor for the converter, how the we select the switch, that is also a major factor. So slowly you will be able to understand, and you can build a converter by yourself also. So this is how the capacitor current. Now I'm discussing the how we can calculate the capacitor, how much value will be there of the we can choose for the capacitor, so that the ripple will be more and more less. So in that case you can see that this is the charging period and the discharging period of the capacitor. So from here we can say that during the on time and off time the capacitor current will be IL minus I0, right? We know that the charge across the capacitor is CV. Okay. So basically if we consider ripple, then this is delta VC is the delta Q by C, the change in the um, charge per unit capacitance. Okay. So the easier way to calculate it by going through the area across it. Okay. So if you're going to the on time area, this is basically a triangle, and if you consider it, then you can see that this is half into the on time current will be the ripple current across the inductor by 2, because we are not taking the whole, taking the half of it. Okay. And t by 2, because we're taking this time as half of the time. If this is the total time, then t by 2, t by 2, t by 2, this is way. So basically, if you calculate it, then it will be delta IL by 8 of f. Okay. Now, if you consider the, if you put the value of delta IL here, then finally we will get delta VC as d1 minus dVs V in, sorry, by 8f square LC. Okay. So this is the conventional way of calculating the ripple voltage. But if you go through any kind of data sheet, any kind of application note of a Texas instrument or analog device, we can see that basically we choose delta VC. They don't have so much time to calculate the capacitor all the time. So they consider it as 2% to nearly 5% of V0. So this will be the limit ideally they considered for the converter design, because they want only 2 to 5% of ripple, not more than that. So you can calculate in that way also, or otherwise you can directly put the minimum of it 2% or maximum of it 5%. Okay. Oh, fine. So we'll design a buck converter, and before we I'm trying to discuss one thing, that is the critical inductance, because based on that critical inductance, what I said, that the discontinuous conduction mode will be happen, because if the critical inductance will be changed in case of the discontinuous conduction mode. So if the value of the inductor is just continuous, since we are only discussing about CCM mode, so if it is continuous, then the minimum current at continuous mode is 0. Okay. So this is basically the total in the average inductor current minus the ripple. Okay. That is equal to 0. So we know that the average inductor current is the load current. So that is equal to this delta IL by 2. We can change it to the formula which we derived, 1 minus d V in by FL. Okay. Now I0 can be written as, since this is a DC, we can retain it as V0 by R, the load resistance if it there. And we can also write it in that way, dV in by R. Okay. That is equal to 1 minus dV in 2 of FL. So equating these two, we will get the critical inductance as R 1 minus d by 2 of Fs. Okay, this is switching frequency. Okay, so this is the value of the critical inductance usually we get for a buck converter. Fine. So now we will design a buck converter step by step by implementing this formula, and try to solve it by yourself, and I will discuss it step by step. Okay. So let us consider we have to design a buck converter which has an input voltage 12, output voltage we are desired to get is 5 volts. So, okay. So we desire to get a converter like this, where the output voltage will be 5 and the input will be 12, and the nominal power will be 100 watt. Fine. So for this, try to first decide the load current. Okay. Try to decide the load current and tell me what will be the load current. I'm giving 2 minutes to everyone. Please try to solve an answer, okay?
₹20.
Write it in the comment box because when we show you. Try to calculate the inductor capacitance, duty. Okay. Okay, fine. I will discuss it. And then we will move into some. See, in this case, the maximum output current will be 20 amp, right? Then this is a DC, so V0 I0 is equal to P0. So that is 100 by 5, that is 20 amp. Now we assume that the maximum delta EL is 40 amp, and this is the delta VC, that is the ripple voltage is 0.05. Okay. So based on which, if we calculate, then the maximum load resistance will be V square by P, it is 0.25. Okay. And the duty will be 5 by 12, that is 0.41. And we consider the switching frequency as 10 kilohertz. Okay. So this is how we have to design some converter. We have to consider these things and have to solve, and then finally we can able to design our circuit in a simulation platform like Spice, like LT Spice, and after which you can apply some parasitics over there, and then we can move into the circuit design in hardware. Okay. Then you can validate it and design the PCB of that, and you can see that it's working like that. Lala. Okay. So for this converter, the value of the inductor will be, you can also calculate by yourself. I put the values over here. So for this inductor rating will be 1 minus dv0 by delta SGS. So we put the values and we get it as 7.3 microhenry. Fine. And what will be the value of the capacitor then? We just put the value over there, formula, and we'll get it at 0.01 farad. So this is how we have to design a converter. Okay. Basically, right? So you have the input voltage, the output voltage. You have to consider the ripple in the inductor, ripple in the voltage, and you consider a frequency, switching frequency at which you want to generate this, and after which you're able to get the value of all the inductor value, capacitor value, and etc. Okay, so this is what the buck converter is. Okay, so try to put the formulas, and after which we'll do a problem. Okay, based on some different converter. So if you have any doubt up to this, you can ask me. Okay, so regarding the buck converter design, if you have any doubt, you can ask, and we will solve a problem related to buck boost converter. And in this week assignment, what was the problem you are asked? Which converter?
It is related to full bridge converter, and
Edge
all
bridge.
44 questions are related to full bridge converter.
Okay, okay. Fine. So we'll solve a problem similar to that related to buck boost converter. Okay. Uh, the rating of the MOSFET, rating of the diode, and I think this kind of question will come, has come in your assignment. So we'll solve a similar kind of problem in buck boost because we don't able to solve the assignment over here. So I'll solve a similar problem, and that will help you in the assignment. Okay. So let me move into that. So this is a problem that this is a buck boost converter. The input voltage and the output voltage is given. The peak output power is given. The maximum ripple in the output voltage is given. And it is said that the buck boost converter should remain in continuous conduction mode up to the range of 200 watt to 400 watt. And let's just consider the inductor current as 10% of load current, and the switching frequency is 50 kilohertz. Okay. Sorry. So based on this data, you have to solve some questions. Like what will be the rating of the voltage of the capacitor, MOSFET, diode, etc., etc. So, have you gone through buck boost converter this week? In the way I discussed. Okay, so you can basically. So, let me derive it for you all. I'm deriving the buck boost equations in a little faster way. Try to understand it. So this was the case when the switch will remain on, and this is the case when the switch will remain off. So this is basically a buck boost converter. That is, it can works as both step down and up. Okay. So here during the on time, this diode will not conduct, right? So the circuit will be just this one. Since this is reverse bias, it will not work. So what will be the output? That will be So VL on equal to E is better to write it V in. Okay. So VL on will be equal to V in. Similarly, IC on will be minus of I naught, since there is no connection between these things, right? So now when the switch is off, this inductor will free wheel across this diode. On that time, the off voltage of the inductor will equal to V naught. And IC off is basically in the reverse way it will flowing. So it is minus of IL plus I naught. Right. So now if we apply volt second balance, if you see volt second balance, that is VL on T on plus VL off T off equal to 0. That is V in dt plus V01 minus dt equal to 0. So if you solve it, you will get V0 as minus of V in d by 1 minus d. So in case of buck boost converter, see that the load is connected in the reverse way. So if it is connected in the reverse way, we consider it as minus, then it will be dV in by 1 minus d. Okay. And if we apply the amp second balance, that is IC on T on plus IC off T off equal to 0, that is minus I0 dt plus this is minus of IL plus I0 1 minus dt equal to 0. We solve it, we will see that the average inductor current will be 1 minus d. So if the polarity is reversed, then it will be IL equal to I0 1 minus d. Okay. Fine. Now if we calculate the ripple voltage current, it will be L dIL dt, that is equal to, in the on time it will be V in. So this is L equal to V in. So the ripple current will be dV in T by L, that is dV in by FSWL. So this is the ripple current. Okay. And the maximum current will be definitely the average plus this, and the minimum will be average minus of this. Okay. So if we calculate the delta Vc, that is the ripple voltage, then that will be also di0 by f of c. How? Because we know that IC on is I0, so dVc dt equal to minus I0. So in this way, if integrate it, we'll see that that is di0 by FSWC. So this is the calculations for a buck boost converter. So now you can able to solve the questions. The first question is the voltage rating of the X component should be how much? X component of what? This converter. The data will be same throughout the question. Okay. So what will be the voltage rating? So this is the data. Okay. Try to copy it for you all. So I'm pasting the data here. Oh, sorry. this question. Okay, I'm giving 2 minutes. Try to solve it in a faster way. The value, the voltage for X as a MOSFET, X as the diode, X as the capacitor. 3 questions. Okay, one by one. Solve and answer it in the comment box. No one yet answered it. Okay, fine. So solve. I will solve it. This is very easy. See, it will be 150. And someone had answered. Take me. Let me check it. Uh, more than 100. Yes, obviously more than 100. So the maximum blocking voltage across the MOSFET and the reverse voltage across diode is also the sum of the input and the output voltage. Okay, it will not be greater than that, so it will maximum value will be 150. Okay. Similarly, I asked another question, right? What will be the voltage rating of the diode? So voltage rating of diode will also same 150, because I said the maximum reverse voltage across the diode is also the sum of the input and the output voltages. Now the next question is, uh, I'm giving 2 minutes for each question. So this is the voltage rating of the capacitor. Try to solve the voltage rating of the capacitor. After 1 minute, I will give a hint if you're not able to solve it. Someone had answered it, so I'm giving a hint. Said that is basically 2% of the ripple plus this. So try to solve it. Now try to solve it and give me the proper answer. Okay. So basically, it will be 101 to 102. Actually, will be 102. It is coming, right? See, the 2% of V0 is 2. Since this V0 is equal to Vc. So it's 102 around. This will be the answer. Okay. Next question. What will be the ripple current of X, where X is the MOSFET? So what will be the ripple current? You can solve it in that way. Okay. As I said that it is I0 1 minus D. So just put it I0 1 minus D. What will be I0? That is the total power by voltage. So the total power maximum is 400 watt. The output voltage was what? 100. So it is 4 amp. So now if we apply the duty, what will be the duty? 100 by 150. That is 2 by 3. So if you apply the duty 4 1 minus 2 by 3, it will be 12 ampere. So 12 plus 10% of I0. So that is 0.4. So 12.4 amp will be the answer. Okay. 12.2 it was given. So 12.2, 12.4 amp. Okay. Next question. That is the ripple current across the diode. See, the ripple current will remain same in case of the diode, in case of the inductor, same. So next question is what will be the value of the critical inductance? So I didn't derive the critical inductance of Bach boost. That was, you can derive it by yourself. Okay. So I'm giving a hint that this formula you can use this, or rather in a very easier way. That's the way I solved, that the minimum resistance you have to choose V0 square by P0 minimum, after which the critical inductance will be 1 minus D minimum by 2 of F switching frequency. Okay. So this is 1 minus 2 by 3. Calculate the R minimum, 2 into 50 kilohertz. So calculate R minimum and tell me the answer. Oh, try to solve. Try to participate and answer so that see what will be the R minimum. That is 100 square by 200. Right. So it will be 50 ohm. So put 50 ohm and the answer will be around 55.56 microhenry. Okay. So at microhenry it will be 55.56. Okay. Next question, you have to calculate the ripple inductance. So formula for ripple inductance is this one. So this is basically delta IL by limit means delta IL by 2. So the formula is in a simpler way is V in dV in by delta IL by 2 into FSW. Okay. One thing to remain, that is the delta IL is, we calculated it as 12 amp. So 10% of it will be the IL is 12. So delta IL will be, we calculate it as 0.4 amp. So put the values. So if we solve it, it will be 3335 microhenry. Okay. So the nearest answer is given the 3333.33. So we calculate it at like this. Next question. The based on the above calculation, if you have to choose the value of the inductance, which will be the value of the inductance you will choose? Okay. These are the values. See, the number 1 and number 2 are definitely cancelled out. So you have to choose between these two. Which will be the most appropriate value? Tell me. At least you can tell this one. We calculate it as 33335. So what will be the nearest value?
D.
Yes, D will be the right answer. Okay. So if you have any doubt regarding the DC-DC converter, you can tell me, and we will do a quick revision of the edge bridge analysis which was discussed. So we'll discuss a little bit about the edge bridge, overview, and we'll end this class. And if you have a doubt in the DC-DC converter, you can ask me here. Okay. So I'm take some time to ask any question. If you don't have any question, we will discuss the, we'll revise the edge bridge analysis class a little bit, and we will end this class today. Okay. Yes. Arvind, you raised your hand. You tell me if you have any doubt. Yes, if you have any question, you can ask. Then we'll move on.
Sir, what about boost converter design? Will you be taking the next session?
Sorry, you asked. You tell me to solve the boost converter also.
Yes, sir. We need the different specifications for boost converter.
It was not discussed today's in this week lecture. Boost converter was not discussed. In this week lecture, boost converter was not discussed.
Yes, it is not a part of agenda, week one agenda.
Yeah, it was not a part of that. So, so we have to move into the next converter. So as you're asking, I'm see you can solve it in that way converter. So it is easier to solve the boost converter then, right? So what happens in boost converter? See, so this is not a part of this course as some.
Yes, sir. In the course, buck converter was there. So,
So you're asking about boost converter, so it was not a part of that. So see, you can solve it in this way. That this is a boost converter, right?
sir, your screen is not visible.
Not visible. Screen is not visible. I think
It's
it's visible.
it's visible.
Yeah, yeah. So try to see it. You ask it, so that's why I'm. So the boost converter is like this. So you have a load like R. So it's L, and this was your switch. Okay. So during the turn on time of this switch, it will be equivalent to uh, like this. Okay. So this is your V in. This is your VL. So as I said that the on time voltage will be V in. Okay. Uh, and when the switch was off, when the switch will be off, then it will be like this. Uh, mm, right. So in this case, it will be VL off, that is equal to V in minus V0. So if you apply that amp second balance, which I said, then it will be V in dt plus V in minus V0 1 minus of dt equal to 0. So if you solve it, it will be V0 equal to sorry, what happened? V in by 1 minus d. So that was the equation of boost converter, and the way I discussed that for ripple, you have to calculate like delta IL. So go through like di dt equal to the on time voltage V in, right? So what happens that the delta IL will be similar to the buck boost converter. So that will be f of L, right? So this is what the calculation of boost converter. Can anyone tell me one thing, that if the duty is 1, then what will be the value of the output voltage in this case? Is it possible, or is it this type of question was asked? It can be asked that if the duty will be 1 in this case, then what will happen? Okay, that V0 equal to Vi by 1 minus d. Who was asking this about the boost converter? Krishna Priya, right? So you tell me that what will be the value of the output voltage when duty will be 1? Okay. Undefined. Is it possible then undefined? It's possible.
Gain will be
Undef-
very high. Means,
you don't need to unmute whenever you are discussing.
yeah, gain will be very high, I guess. Kind of spike.
Uh, See, the basic principle of a DC-DC converter, that is chopper. That means you should have a duty. Otherwise, if you have a continuous duty, that means you're giving a continuous pulse to a switch, then it will not behave as a converter itself. That is the first thing, that it will not work as a converter because you're giving a continuous switch on. Then why? How could it be uh, behaves like a converter? And next thing is that practically it is not possible that your duty is one. So uh, that undefined thing will not happen. That if you consider the curve of your output with respect to duty, then it will be not zero. It will not going to zero or undefined due to the parasitics. Due to the parasitics on the capacitance, and if you're designing a PCB, then it also some kind of parasitics were there also. Fine. Okay. So someone asked about the boost converter. Is understandable? So I just discuss a little bit because it's not a part of your course. Okay. So I'm revising the edge bridge a little bit. So in case of edge bridge analysis, you see that there will be 4 switch. So this is IGBT. So you can use a MOSFET also. Fine. So you have 4 switches. The possible switching combination can be either TA plus on, TB plus minus on, TB plus, TA minus. So if you see that the upper 2 switch will be on, then it will get, the path will be like this. So this will not able to flow on that way, right? So the possible switch combination, you see that one is TA plus TB minus. That means in this way can return. Another is TB plus TA minus. That means the diagonal switch will remain on. Okay. So if in a case it happens that the upper switch or 2 switches or these 2 switch TA plus TA minus will get on at the same time, then it will damage, right? Then the shoot through phenomena will happen. So that's why in case of inverter design, whenever you are using a switch like this, uh, whenever you have a bridge, and whenever you have a half bridge or full bridge, the leg you are using, there uh, there will be a the on time of the both the switch is not same. Okay, there will be a delay, and that is called the dead time or dead band. So otherwise it will get short. So definitely you have to give the pulse in that way that this and this will not on at the same time. There will be a certain delay of nanoseconds or some sort of seconds, right? Okay. So if you see from the edge bridge analysis, when these 2 switch are on, you can see that the output voltage is VDC, the output current is minus of I naught. When upper 2 switch is on, then it gets shorted, right? So the output voltage is 0. So it doesn't have any mean that these 2 switch will operate at the same time. When these 2 switch is on, then the voltage across this will be 0, since you can see that the same loop is forming, right? So it will be like a open circuit. It will behave like the, sorry, like a short circuit. Ice is 0, and at the same time it's behave as open circuit also. This is also 0. Okay, the voltage blocked by the non-conducting devices will definitely must be equal to the ADC. Okay, so this is how it behaves, and this is in case of the H-bridge analysis. We give a pulse, reference pulse. This is the reference signal. Another one is the modulating signal. Based on which we get the pulse which we are desired to give at the switch. So it may be two types. One is bipolar, another one is uh, unipolar. In case of bipolar, what happens? Suppose, mm, see this one. In case of bipolar, this is happening. That this is my reference is sinusoidal. Okay, and in the reverse case, we'll applying a reverse sinusoidal signal. Okay, so that's why this it has two poles. So it is called a bipolar signal. So the logic is that whenever it gets greater than the reference signal uh, is greater than that of the modulating signal, then it will getting on, right? So this is how the pulse are forming, which pulse you are giving to the switches, and in this way the switch will be turned on and turned off to make behave as a uh, converter. So this is basically bipolar. We applied it in inverter cases. Okay, so this is the modulation index, the output voltage by the reference DC voltage. This is the modulation index. And I hope these calculations are done in the class this week, right? So I'm not going deep into it. Uh, so this is how the nature of the output current will be. So this is the ripple. If you see, and this kind of ripple will be found at your output. Okay. In bipolar case, there are more ripple. Okay. So we just have to consider the average of it, which is given in the dotted line. So this is what the output current will be, and the DC current will be definitely fluctuating, but if take the average of it, then it will be like this. Okay. So now in case of the unipolar, um, there are two references I are giving. This is for the A and for the B. In that way, we're also giving or another way you can do it in the sinusoidal modulations. You can change it that SPW wave. Okay. So in this case, what happened? The reference one is V out by 2 VDC by half plus half. PV is also inverse of that. Now here, you see that we are giving two sinusoidal pulse over here. Okay. We're giving two sinusoidal pulse. So when this one is greater than the reference, then we are getting this pulse. And when this one will happens, that is negative of the triangle, we remember triangle if you have sign, then this one will happen. So ultimately we get a set of voltage like this, and this will be our output current. Okay, I'm not going into the equations, just try to understand the nature of it. Uh, so basically bipolar versus unipolar is that the main fundamental difference is that whenever we deal with a bipolar, the bipolar has more switching ripples than considering to unipolar. Practical if you do that things, and you see that there is a continuous pulse we are getting here in the bipolar. It's like this, and in unipolar we'll get this kind of nature. If you take the average of it, bipolar, it will be different, but the more or less current will be remain same. But you can see that at unipolar the ripple is lesser than compared to the bipolar. The bipolar has a more ripple. So okay, current ripple is over unipolar, which I mentioned over here. And so since here the switching frequency is twice of it, so definitely filter requirement required in case of bipolar, which is not required in unipolar. And the voltage, transition voltage at the unipolar is twice of the bipolar. Okay, so the both have some different applications so for using it. So these are the equations which I think discussed in the class, so you can put the equations to solve the assignment. So that's all for the day. So the HBG is an inverter, and for next week we'll go more deep into the design of the converter. So I hope you all understand the basics of the DC converter, and we revise a little bit about the H-bridge inverter. Uh, there are a lot of things you have to understand in the H-bridge inverter. So I didn't go deep into that because you already this was discussed by the course instructor in the class. So it was you have to more know about the Fourier analysis, after which you can able to do these things. Though to try to revise the basics of the Fourier analysis like quarter wave symmetry, half wave symmetry, this type of things, and then you can able to solve these things, right? So so that's all for the day. So if you have any overall doubt, so you can ask me and we will close the session. Yes. Okay. Try to solve those assignments properly. So that's all. Any doubt? If you have any doubt, you can ask. Otherwise, you can drop. Okay. If you have any doubt, you can ask. Otherwise, you can leave the class. Okay.
Hello.
Sir,
Yes.
sir, whether the video clip available to see the details, sir?
Sorry, I didn't get that. Can you say it in a little slower way?
Yes, I came late, sir, due to for some reason.
Can you wrote it in the voice? That will be cracked. You can note it in the comment box.
Okay, sir.
Yes. Next.
This bipolar and unipolar, which is more preferable? Like, for which case filter design is easy?
As I said that in case of the unipolar, there is a lesser repel, so you don't need to have a filter itself, right? And they has a different function, that where you have to use bipolar, right, and where you have to use unipolar. Okay, there are some applications where you can use that things. Okay. The basic difference is that as I said that the unipolar PWM are basically better. It has a better efficiency, better lower THD and all. Okay. Yes.
Yes, understood. Thank you.
Yeah. You didn't up. Yes, you asked the question. Can you wrote it over there in the comment box? You raised your hand, right? Renuga. Mm. Renuga, you can put your questions in the comment box. I'll try to definitely answer it if I know that.
Sir, I missed the video clip, sir. From the starting itself, I want to see the full lecture, sir. Is there available?
Okay. I will share it in my YouTube. You can show from there. I will share the link with the NPTEL this week, or from the
Okay, sir.
next week. I will share the link. Okay.
Okay, sir. Thank you.
I will upload it by tomorrow. Okay. So you can see over there.
Okay. Thank you, sir.
Okay. So if you don't have any doubt, I'm dropping the class right now. Okay.
Thank you, sir.
Okay. Thank you, everyone. Good night.